Hello and welcome to a new chapter that we will be starting today, and this is chapter number 8. So, as far as the course is concerned, we are sort of shifting gears today, and in the next two chapters, we will be talking about a new sort of area in operating systems, which is called memory management. Okay. So chapter number 8 and chapter number 9, based on the ninth edition of the Silberschatz Galvin Gagné book, are dedicated to management of memory. Okay. So up till now we have talked. Last couple of chapters were on process management. So in chapter C, in chapter 3, we saw how we could create processes, and some system calls for process interaction. And then chapter 4 was about how within a process we can create many threads, and then they can sort of do parallel computation. Chapter 5 was all about scheduling, picking the next process for execution on the CPU. And then chapter 6 was looked at synchronization issues among processes. So when multiple processes are reading, writing to or from a common shared data, then depending on their read write patterns, we can have race conditions. So now we sort of shift gears and talk about an extremely important area of operating systems, and this one deals with memory management. Okay. So I'll first read the introduction for this section called memory management. So this is from the textbook, and it says that the main purpose of a computer system is to execute programs. So we already know that we have a set of hardware resources. We've got our CPU, we've got our main memory, we've got other kinds of memories like cache, registers, and so on. We've got our disk, right? And we've got our I/O devices. So main goal here is using those hardware resources, execute programs. So these programs, together with the data they access, must be at least partially in main memory during execution. So we already know that if we want to execute any kind of application, we need to bring that application into main memory. Okay. So we don't have, we can't execute directly from the secondary memory of the disk, right? So disk accesses are very, expensive. So we have to avoid them as much as we can. But again, here is a trade-off, because main memory, although the access times are low, but the cost is very high. So we can't afford to have something like 512 GB of main memory of RAM. That would make the cost of the machine really expensive. So we have a small amount of main memory and a large amount of disk, and we have to sort of execute programs so that we try and get the best of both worlds. Our response times are as low as possible, and looking at the program behavior, can we sort of do some optimization, right, among the usage of the main memory and the disk. Again, what kind of optimizations are we talking about? This will be clear as we move on in the discuss the next two chapters. So main thing here is the programs along with the data that they access. So both code and data instructions must be brought into main memory during execution. So you bring the data and instructions into main memory, and then you can execute the program. Okay. Modern computer systems maintain several processes in memory during system execution to support multi-programming. Many memory management strategies or schemes exist, reflecting various approaches, and the effectiveness of each algorithm varies with the situation. So there are many algorithms for performing memory management, and we'll try to cover at least the most important ones. Selection of a memory management scheme for a system depends on many factors, especially on the system's hardware design. Most algorithms require some form of hardware support. So many times we'll see that whichever memory management strategy you want to pick, you do need hardware support for that. So that is very important. Okay. You may want to, you may have a very nice memory management feature, but the hardware may not support it. So that sort of is, the hardware support is very important. Okay. And selection of memory management scheme depends on various factors. Okay. So different kind of systems, we can have different kind of memory management strategy. Memory management in a large supercomputer may be different from memory management in a desktop machine, which may be different from a memory management in a laptop machine, which may be different from a memory management scheme in a mobile phone, and which may be different from a memory management scheme in a smart watch, in a smart fridge, in a smart car. So the application sort of guides the memory management algorithm. Okay. So with this, now we start our discussion on chapter number 8. Okay, so now I am on slide 2. So I don't know how many of you have heard about Sir Arthur Conan Doyle and Sherlock Holmes, one of the famous fictional detectives. If you haven't, then it would be a good idea to check out some of these books. They are available free. So in one of these books called Hounds of Baskervilles by Sir Arthur Conan Doyle, with Sherlock Holmes as the main protagonist. Let's look at this particular quote. I cannot guarantee that I carry all the facts in my mind. Okay. Intense mental concentration has a curious way of blotting out what has passed. Each of my cases displaces the last. So what is being said over here is the memory capacity in the detective is finite. So which means that the memory can process only a limited amount of cases at a time, right? So he or she works on a case, is thinking about it, and then solves the case, and then moves on to the second case, and moves on to the third, moves on to the fourth. So importantly, a new case sort of erases or replaces all the previous cases. Okay. So what is the significance of this quotation? Significance is very similarly as they have mentioned here. Main memory is also in a limited quantity. Okay. So access times are very quick, but the drawback is the memory as such, main memory is expensive, of course, due to the quick access times. So main memory is expensive, so therefore we don't have enough main memory to bring all the programs, all the data inside, right? So therefore we have to try to use main memory as carefully, as intelligently as possible. Okay. So it's a finite resource, so we have to be very smart when we are using it. Okay. What are these smart algorithms? We'll soon see. But main point over here is main memory is not enough to accommodate all the applications that we want to run. We can probably accommodate them in parts. Okay. So again, how do we optimize this memory usage? So this is what this chapter and the next is all about. Okay. Okay. Now I am on slide 3. So by now we all know about this multi-programming, right? So we have seen in earlier chapters that the CPU can be shared by a set of processes. Multiplexing CPU and I/O execution, right, among many processes, and for maximizing the CPU utilization. So this is multi-programming, key OS feature which every operating system that we look at implements. What do we gain by using multi-programming? Of course, we improve the CPU utilization. We know that, right? Because if a process does CPU for a while and then goes off to do I/O, without multi-programming, we will not give the CPU to any other process, and we have to wait for the I/O of the first process to complete. So our CPU will be idle most of the time. So the idea is, as soon as one of the processes or the process that is running, assuming a single CPU needs to do I/O, we do a context switch and we give the CPU to some other process which has some CPU burst which has to be executed. So we improve the CPU utilization, and we can improve the speed of a computer's response to its users. So assume we have many processes and each of them belong to different users. They are all sharing a CPU. So then with multi-programming, obviously in a particular time unit, more work can be done, more programs can be executed, and therefore computer response time also improves. Right. So if we don't have multi-programming, we have two users, process 1, process 2. User 1, process 1 is doing CPU, then goes off to do I/O. Without multi-programming, we have to wait for the I/O, which means it will be a long time before the user 2's process even starts executing. But with multi-programming, user 2's process can start executing as soon as user 1's process goes off to do I/O. So obviously response time also is being improved. So in order to, again, as we know, in engineering nothing comes for free. Any kind of gain that we are achieving due to any concept or philosophy, there is always a price to be paid. So what is the trade-off here? If we want to maximize the utilization, if we want to improve the speed of the computer's response to its users, if we want to implement multi-programming. So the overhead is we need to now keep several processes in memory. Okay, and so then we have to figure out which process we have to keep in memory. Because without multi-programming, we can do with only one process in memory. Our memory management becomes very simple. But to support multi-programming, now we have to, because we have to keep multiple processes in memory, so our memory management becomes more complicated. Because now we have to answer the question that which process or which processes are going to be kept in memory and for how long. Okay, so we'll try to answer that. So in other words, several processes share memory. Clearly, memory management becomes more complex. Right? So it's clearly more overhead for the OS memory manager. So there's an important component of the operating system, memory management unit, MMU. Okay. So in this chapter, we will discuss various techniques to manage the memory of a system. Okay. And all of these techniques, as we mentioned earlier, will require some form of hardware support. So as we discuss each technique, we'll see the kind of hardware support that is required for that technique. Okay. Okay, so now I am on slide 4, and this is an outline of of this particular chapter, memory management strategies. So we first start with some background introduction. Okay, as usual. We will look at introduce some of the basic hardware that is needed for performing memory management. We will discuss the concept of logical address space and physical address space, and therefore a logical address and a physical address. Okay, so some of those introductory concepts which are going to be used again and again, later in the memory management algorithms, we will discuss in the background introduction. Then we will discuss swapping. So taking a process and copying it from disk to main memory or from main memory back to disk. So we'll discuss swapping. Then we'll discuss contiguous memory allocation. Okay, so our first and most and the simplest memory allocation strategy, contiguous memory allocation. Okay, so we'll see how this is performed along with some examples, some trade-offs, some advantages, some disadvantages. First memory management scheme, contiguous memory allocation. Then we'll talk about paging, our second memory management scheme. And within paging, there's a very important data structure needed to support paging. That's called a page table. So we'll talk about page tables. Next, we'll talk about another memory management strategy called segmentation. So a lot of times when you may be doing C programming, you may have encountered this segmentation fault, right? So we'll learn about what the segmentation is. And finally, we'll do some case studies in which we will discuss the memory management strategies that are employed in many of the real life systems, such as the Intel Pentium chip and the ARM chip. Okay, so as you can see, main crux over here is to discuss various memory management strategies. Okay, now I am on slide 5. As we know, each chapter has some learning objectives. So what are the learning objectives for this chapter? To provide a detailed description of various ways of organizing memory hardware. So this is the first part. We talk about the hardware that is needed to implement these memory management strategies. So we'll talk about different kind of registers. We will talk about different kind of addresses, right? Logical versus physical, right? And other kinds of hardware. Okay. So various ways of organizing memory hardware. Next, to discuss various memory management techniques. Two of the most important ones that are used, which we will discuss in great detail: paging and segmentation. Okay. So some systems may use pure paging, pure segmentation, or some systems may use a combination of both. Okay. And finally, our case studies: Intel Pentium processor, and we'll also do ARM. Okay. So if I just go towards the end, so we'll do Intel Pentium, we'll do ARM, and we may even look at x86 CPU as well. So we look at various kinds of processors and the memory management technique they propose. So do they use paging? Do they use segmentation? Do they use both? In a combination. And what do their memory addresses look like? 32-bit, 64-bit. What are the constituents? Okay. So these are the objectives. Talk about the hardware. Discuss some memory management strategies. And then look at the case studies, which will show for real life processors what kind of memory management do they perform. Okay, so these are the learning objectives for this particular chapter. Okay, so now I am on slide number 6, which is titled background. Okay, so now if we spend some time and think about how is our computer memory structured, right? So I'm sure you would have done GE 103, in which you looked at or did programming with pointers, right? And so as such, pointers are special kinds of variables that instead of storing regular values, they store what? They store the address of another variable, which could also be a pointer, of course. So in that, in that course, and also in the if you took the computer architecture course, which you would have seen the studied the structure of memory. So here, what we have is memory consists of a large array of words or bytes, each with its own address, right? Okay, so large array of words or bytes, each with its own address. Okay, so one way we can, so it depends on the system, but One way we can visualize this is that you have these array of cells, array of memory cells. Each memory cell has an address, memory address, and in each cell we have, let's say, one byte worth of data or instructions. So 1 byte means 8 bits. So if I want to store an integer, so the size is what? So 32 bits. So I'll need 4 of these cells, and then each of these cells will have an address. And if I store it in an adjacent manner, so 100, 101, 102, 103. So between memory addresses 100 and 103, both 100, 103 included, I have my integer living. So one address, one cell, 1 byte, 8 bits. So 4 cells, 4 addresses, 4 bytes and 32 bits. Okay, so again we have a large array of memory cells. Each cell has its own address, and each cell can hold some piece of data. Let's say 1 byte. Okay. So, and we also know that we learned about the interaction between your memory and the CPU. So whenever you need to execute some program and then some data with it, so that program and its data will be stored somewhere in the memory. So then what the CPU will need to do is, the CPU will need to fetch instructions from the memory according to the program counter value. So program counter will have next address at which the CPU goes to fetch the next instruction. Like this, it can fetch data also, and these instructions may cause additional loading from and storing to specific memory addresses. So one can load from or pull out a value from a memory address, bring to the CPU registers, or one can store a value to the memory address. Okay. And we all know about this instruction execution cycle. So here again we're just revising the architecture concepts. First, fetch an instruction from memory. Right, instruction is then decoded. Right, so again it's a 32 byte instruction, a bunch of zeros and ones. So as you would have studied, the instruction has certain parts. A certain number of bits may be reserved for what kind of instruction it is, addition, subtraction, whatever. Some bits may be reserved for the operand values. So if you're adding two numbers, what are the values of two numbers, right, and so on. So you do the instruction decode, and that decode may cause operands to be fetched from the memory. So let's say first you load the instruction, and then if the operands are not there in the instruction, then maybe that instruction will cause the operands to be loaded again from the memory. Okay, and then after the instruction has been executed on the operands, the results may be stored back in memory. So again we talked about this in chapter 1 also. Instruction fetch cycle. Fetch an instruction from memory, decode it, perhaps fetch the operands, execute the instruction, store back the results. So once again you have interaction happening between the memory and CPU here. Okay, and we also know that there is a sequence of memory addresses in which a process or each process is stored and executed. So sequence of memory addresses, a block of memory in which each and every process is stored and executed, basically lives there. So what is this block called? It's called the address space. Right? So we know each process has an address space, and that process, while it's executing, lives in that address space. All of its instructions are there, all of its data is there. Okay. So these are some of the background information. Structure of memory organized as cells, each having a byte. Interaction between the memory and the CPU. Instruction fetch and instruction execution cycle, and process address space. Okay. So I hope all of these are clear, right? All right. So now I am on slide 7, and here we're still talking about background and basic hardware. So we know that as far as direct accesses are concerned, right? As far as direct accesses are concerned, the CPU can directly access only the main memory and the registers. Right, for now, The others can also be there, for example cache. But main important point is the CPU cannot directly access the disk memory. Okay, disk accesses are very expensive, and anyway we want to minimize as much as possible. So which means that programs which are in the disk need to be brought into main memory before they can be executed. So in a way we know that main memory is volatile, disk is not. So the permanent place where the all our programs live is in the disk. Now whenever we want to run a program, or whenever the CPU wants to run a program, the program has to be brought into the main memory from the disk. Okay. So any instruction that needs to be executed, any data needed by the instructions must be in one of the above direct access storage devices. Okay, main memory registers. Okay. So most CPUs can execute simple instructions stored in registers at a rate of more than 1 per clock cycle. So clock cycle is a very small unit of time, and most CPUs can execute at least one instruction which is stored in the registers, mind you, per clock cycle. However, when you want to access the memory, then completing a memory access can take many cycles. Let's say perhaps 100. So as we studied in chapter 1, we have a memory hierarchy, and then the registers are fastest, followed by perhaps cache, then main memory, then disk. So if you have something in registers, the amount of time to access that data is, will be very less as compared to accessing from main memory. Okay, so for registers, the execution rate could be greater than equal to 1 instruction per clock cycle, whereas for a memory access operation, it can take maybe 100 cycles. Okay. So in such cases, the processor normally needs to stall, since it does not have the data required to complete the instruction that it is executing. So because you need instructions or data from the main memory, you can't keep everything in registers because of the cost. So for memory access, while you're doing that, the CPU is stalled. It doesn't have enough data. Okay, and note that this problem is particularly severe because of the frequency of doing these memory accesses. So these memory accesses have to be done, a lot of times, very frequently. So naturally, that overhead and performance degradation will also be great. If there's some task which takes a lot of time, but you're doing it infrequently, it's still tolerable. But if that task is happening very frequently, then obviously you have a performance problem. Okay. So then naturally what we do is, in these cases, we add a memory in between the registers and the main memory called the cache. So memory buffer called cache, and then we try to predict what will be the data or instructions used in the future, and then we try to bring those into the cache, and then we try to pull them from the cache. So cache accesses are much faster than main memory accesses. Okay. So again, we will talk more about the cache when we discuss paging. Okay. Okay, so now I am on slide 8. So in the previous slide, we saw that one issue is memory accesses can take a significant amount of time, right? Or to be more precise, the memory access time is quite significant. And because of the high frequency of these memory accesses, overall system performance may not be very good, right? So one solution is to introduce a cache memory in between the registers and the main memory. So whenever you have to have a memory access, see if the data is available or the instructions are available in the cache. If yes, then the access time is quite less, right? So of course, there is a concern regarding memory access time, right? There's another concern regarding memory, and which is memory protection. So we discussed that each process is assigned a block of memory, which is called the address space of that process. This is assigned by the operating system, the memory management unit. Now, by default, a process cannot access another process's address space by default. Sometimes this needs to be allowed, for example, for shared memory. So if I have a process and I want to share some data with another process, then I set up the shared memory. But by default, this address space for each process is protected, which means that another process by default is not allowed to enter into the address space of another process. So we need to ensure correct operation to protect the OS from access by user processes, number one, and also to protect user processes from one another. So there are two security issues. One is the user processes need to be protected from each other, which we just discussed. So which means process cannot be allowed to, a user process cannot be allowed to enter the or to access the address space of another process by default. So that is one thing, protecting user processes from one another. In addition, we also need to ensure that user processes cannot access the address space of kernel processes. So note that kernel processes also have their own address space, and what we don't want is a user process accessing the address space of a kernel process, and even worse, trying to make modifications there. So like changing the scheduling algorithm or writing some junk, right? So we need protection of the OS from user processes, or more precisely from the kernel process address space, right? We need protection of that from user processes, and also we need protection among user processes so that they do not enter into each other's address spaces. So this protection is needed, right? So how do we ensure this? So we ensure that each process has a separate memory space, separate address space, and the process should be able to access only the memory addresses in its space. So very simple. Let's say the address space of a process starts from 100, goes till 1000. So now if while that process is executing, naturally we'll have memory accesses. Why? To grab instructions, to grab data, to also do store, to do loads and stores. So if you have an access for 100, could be okay. Access for 1000 could be okay. Access for 500 could be okay. Access for 2000, that is out of bounds, should not be allowed. Okay. So we have to ensure that the process is able to access only the memory addresses within its address space. Okay. So this is a hardware solution. OS does not intervene between CPU and its memory accesses due to the performance overhead. So this is purely a hardware solution, whatever we are discussing right now. Generally the OS, we know the OS is a piece of software. So whenever you're calling the OS to intervene, so generally that will have extra overhead. Okay. Because of those system calls and all those things. But if you have a total hardware solution, even using assembly, you can have that hardware solution, and then its performance will be much better. So we are not involving the OS between a CPU and its memory accesses. So what exactly is this hardware solution? It uses two registers for a process. One is called a base register, and the other is called a limit register. Okay. So base register holds the smallest legal physical memory address. Okay. So soon we'll discuss the concept of physical and virtual memory. But for now, let's assume physical memory is our main memory. Okay. So smallest legal physical memory address which is allowed is in the base register. So lower bound. Limit register specifies the size of the range of the legal memory addresses. So the range is in the limit register. So once again, base register holding the smallest legal memory address, limit register specifying the size of the range of memory addresses that are legal. So if you step out of that range, it will not be allowed. To give you an example, if the base register holds 300040 and the limit register is 120900, then the process can legally access all addresses in the range of, so from the base register 300040 and then adding the limit to the base 4209390. So put it simply, if the base register contains 100, okay, which may be unrealistic because that 100 location is generally reserved for other kind of tasks which we will not get into right now, but just assume base register value is 100, limit register value is 1000. Okay, so base register 100, limit register 1000. So what is the range of legal memory addresses? 100 to 1100. Okay, so base register 100, limit register 1000. So range of legal addresses which are allowed is 100 to 1100. Okay. The OS memory manager allocates the address space. So part of the memory management unit, it will, whenever a new process comes, it will see, it will have a map of which memory is available, which is not available. Among the memory which is available, it will see how much of memory can we give to this process, and then once it makes that call, we have the address space. Okay, so we have a base register and a limit register. Okay, so now I am on slide 9. So now using this base and limit register, how can we ensure this protection of a process's address space? So question is, how do we ensure protection of the address space of a process? So what we do is we compare every address generated in user mode with these registers. So we'll have a string of memory accesses, string of accesses generated, right? And each of so we'll have something like 100, 101, 102, 103, and so on. So what we're saying is, in each step we are trying to access this particular memory location, and once we get access to the data, we are probably either doing a load or store. So we all know that from architecture course. So what we do here is every address that is generated, right, is compared with these registers. Okay. So any attempt by the program executing in user mode to access OS memory or other users memory results in a trap. So if you go out of bounds, a trap results, an addressing error, and that access is not allowed. So maybe you get a message saying that you're going out of bounds, this belongs to or you're accessing some memory which you're not supposed to. Okay. So in the next slide we'll see, using a picture, how we ensure this, right? But what we do is, for each memory access we check with the base and limit register values. If it's within bounds, we go ahead with the access, otherwise we don't allow it, we have a trap. So base and limit registers can only be loaded by the OS, which uses a special privilege instruction. So naturally these base and limit register values need to be loaded for each process. It is done by the kernel, and of course the instruction which the kernel uses to load these base and limit register values is of course privileged. Okay, executes only in kernel mode. Hence the OS can change the register values, right, but prevents user programs from changing the register values. Okay. And as we know from the earlier chapters, OS is given unrestricted access to both kernel and user memory. This allows it to load user programs into user memory, dump out programs in case of errors. Okay, so each address that is generated is compared with the base and limit registers. If it is within bounds within the address space of the process, the memory access is allowed. Otherwise, it is not, and it results in a trap or addressing error. Okay, so let's see using a picture how this works out. Okay, so now I am on slide 10. Here we are showing the base and limit registers for a process, or for one particular process. So this is a snapshot, an image of our main memory, or what we call our physical memory. So we can see in the starting memory instruction, starting with 0 to 2,56,000, we have the OS stored. Okay, so these many memory locations, and if each of them holds a byte, then this is the size in terms of number of bytes, right? So 1, 2, 3, 256k kilobyte, and then we have a bunch of processes within main memory, right? And for one particular process, the base register is, as we discussed these numbers earlier, we are using the same numbers here. The base register value is 30040. Okay. So for each process we have a base register, and for this particular process in question, value of base register is 30040, which means it's a starting memory address, which means the address space starts from this memory address. Limit register is 120900. Okay. So we, as usual, we add this to the base register and we get the last memory address. So 30040 plus 120900 is 420940. So now we have the address space of this process. Okay. So once again, base register holds the smallest legal physical memory address, or we can say main memory address, smallest legal one, and limit register specifies the size of the range. So obviously, in this address space we have a range of addresses, 100 to 1000. It's a range. So that range is specified using the limit register. So now it's clear, using the base and limit register values we can get the boundaries in terms of memory locations for a process. So for this particular process we can say its range is 30040 all the way to 420940, and then we can see, just subtract one from the other, that is the size of the address space. Okay, so I hope this is clear, right? Base and limit registers for each process, and consequently address space for each process. Okay, and we can see the last location here is 1024 into 10 raised to 3, so 1024 kilobyte. So looks like it is 1 MB. That's what it looks. Okay, the whole memory. Okay, so now I am on slide 11, and now we see how these base and limit registers provide protection. Okay, so let's say now what has happened is, we look at a couple of events. What has happened is we want to execute a process, so which means that process has been brought from disk into main memory. It's gotten an address space, all done by the memory management unit. How it does it, we'll soon see. And so it's got its address space where the process and its data has been brought, and now it's time to execute the process by the CPU. CPU will execute the process, and what will happen is we will have a sequence, a series of memory accesses: memory access 1, memory access 2, memory access 3, memory access 4, and so on, for this particular process. So for each memory access, we are trying to go to a particular memory address, right? So we go for a when we go for a particular memory address, we take that address and first we compare it with the base register. Okay. So what do we need to see for the operation to be valid? When we are comparing the memory address that has been generated during the program execution, when we are comparing it with the base register contents, what kind of a relation do we want between the base register contents and the address generated or the memory access? The memory access address has to be greater than or equal to the base register value. If it's less, then obviously we are out of bounds from the left hand side. So if my base register contains 100 and my access is for 99, obviously out of bounds. So if the memory access I am doing, if it's greater than or equal to the base, then I will I'll trap to the operating system. Okay. So there I am checking the lower bound. Okay. So note that addresses start from 0 and not 1. Right. So I don't have I don't have 1 to 10. I have 0 to 9. Okay. And if this condition is satisfied, then I have to obviously check at the other end. Right. It should not go out of bounds at the other end. Answer is yes. Then I add the base plus limit, because the base plus limit will give me the outer bound. So if my base register is 100, limit is 1000, then I see what the access is. If it's for 101, right, I compare 101 with base plus limit. 100 plus 1000, 1100. So if it's less, we go ahead, which means I'm this memory address access is within bounds. We go ahead and do that memory access, do whatever load or store, whatever you want to do. If no, again trap to the operating system. This is a addressing error. So operation is very simple. The address I'm checking it at both ends of the range. So if my range is between x and y, then my memory address should not be less than x, and it should not be greater than y. Okay. So if it's within that range, the memory access is allowed. If it is not, if it's out of bounds, either on the left side or on the right side, right, either on the lower bound or the upper bound, we trap to the operating system and say it's an addressing error and it's not allowed. So using this base and limit register, we can easily ensure that we have protection. So whenever a process is executing and we are generating or we are accessing memory addresses inside that process address space, we have to ensure that we don't go out of bounds. So this will ensure that. Okay, I hope it's clear. Right. Okay, I'm now on slide 12. So before we move on, let's do a very simple example of this address protection using base and limit registers. So let's say base register value or BR is 100. Okay. So which means smallest legal address is 100 for this process. And limit register value is 10, which means size of the range is 10. So what is the range of memory addresses, legal memory addresses? Note that it is not 100 to 110. it is 100 to 109, because memory location starts from 0. So here also going from 100 to 109, we'll see that these are 10 memory accesses. So the range is 100 to 109 and not 100 to 110. So both are inclusive. So 100 is allowed, 109 is also allowed. So let a memory access be denoted as ME, short form. So now the equation we have is ME is greater than equal to BR, right? And ME is less than BR plus LR. So which means ME is greater than equal to 100 and ME is less than 110. So which means that 100 is 100 within bounds or out of bounds? 100 is within bounds. What about 110? 110 is out of bounds. Okay, the last legal access, the last legal address which is can be accessed is 109. So I hope now the greater than equal to with the base and less than with base plus limit makes sense to you. Okay.